I want to draw a couple of pictures here, and I want you to tell me what to do with each of these pictures. Let's say that I have object number 1 moving to the right, and it's going to collide with object number 2 that is at rest. We're going to say its velocity right now is 0 meters per second. Let's say that after they collide, because they have Velcro on them or because they're just sticky or whatever, they stick together and head off as one object after this collision. How would you analyze this collision? I'm not saying what's the answer because we don't have any numbers here, right? But if we did have numbers, what would we do with it? What's the concept that we would probably use?
The equation we used earlier, but only one term.
Well, you could use impulse. You could use impulse and analyze either object 1 or object 2. But in all likelihood, you're going to use conservation momentum, Pi equals Pf, analyzing both objects. M1 V1I plus, what do you want to say that the momentum of object 2 is before the collision? It's at rest, so its momentum is 0. Hey, they stick together, it becomes MVF, right? Total mass times final velocity. You're in all likelihood going to solve for VF here. Right? That's not new. You did that, what, 7 times on your worksheet yesterday? We did 3 example problems yesterday with this. It's no different than the questions that we did earlier today for review. One object collides with another, Pi equals Pf. All right, let's take a look at another scenario here. This time, let's say object number 1 is at rest, and object number 2 is moving downwards towards it at a certain velocity. They collide, they stick together, and then they head off as one object after this collision takes place. We're going to do the same thing, right? Pi equals Pf. We're going to say this time 0, because object number 1 is at rest, plus M2 V2I equals, they stick together, so it becomes MVF. Solve for VF, and whatever we get there. Is that all right? Again, nothing new there. You spent all of yesterday's class learning about this, and then we spent another 25 minutes or so checking over questions today based on this exact same thing. Nothing new. What happens, though, and this is where it becomes a little bit new, what happens if object number 1 is moving to the right, as we have right here in scenario number 1, and object number 2 is moving downwards like this, as we have right here in scenario number 2. Let's say these 2 objects hit each other at this point right here. They stick together and head off as one. Where are they going to go first? Where's the wreckage going to go? Ballpark. Like, not exactly. You can't give me an exact angle, but... Sorry, diagonal to what? Okay, but which direction diagonal? Kind of southeast? Yeah, it's not exactly southeast. Not likely, at least. But it's somewhere down in that general vicinity. We're going to deal with this. All right, go ahead, Nick. Okay, yeah, we are going to have to do that, but not quite yet. Because, I mean, you're dealing with the hypotenuse here, but this doesn't actually combine with this to give me this, not in terms of velocity anyways. Here's what I want to do. You go ahead, Nick, or Brian. Oh, yeah, not impulse. I want to do momentum. Okay, I want to do conservation momentum here, but I want to do it for the x and the y-axis. Watch really carefully here, okay? Watch real closely what I'm about to do. The x component can be described by this. It's exactly the same thing as the question that we just did. Why? Because if object number 1 is moving to the right, and object number 2 is moving downwards, as long as I'm analyzing the x component, the horizontal, it's as if object number 2 isn't even moving, right? How much of this velocity is on the x-axis? None. None of it is. So if none of it's on the x-axis, you might as well say it's not moving. You might as well say object number 2 is at rest. And the analysis becomes exactly the same as we did in scenario number 1 there. So what about the y component? Well, when you're analyzing the y component, object number 2 is moving downwards, while object number 1 is on the x-axis only. It's as if it's not even moving, right? As if it's not moving, or it's as if it's not moving, we might as well treat it like we did over here when it truly wasn't moving. So let's take our analysis that we did over there and move it over here. Now we've solved for an x component of the final velocity and a y component. Now, Nick, what do you think you're going to do with it? Yeah, now we're going to do what Nick said earlier, which is draw a triangle. We have an x component goes this way. We have a y component that goes this way. And the hypotenuse goes right here. How are you going to solve for that hypotenuse? Pythagorean theorem, right? And how are you going to solve for the angle? We need the angle because there's a direction associated with momentum. The inverse tan function of opposite over adjacent. Okay, let's have a look at our example, and then that's it for us for today. The example says a 1,200 kilogram car traveling north at 10 collides with a 1,500 kilogram car traveling west at 12. So let's draw this here. Here's our car number 1. Its mass is 1,200 kilograms, and its velocity to the north is 10 meters per second. We've got another car going to the west at 12. And its mass is 1,500 kilograms. It is so important that whenever we see two different dimensions, north and west, in the same question, that we break it up into x and y components, that we draw this picture and go x and y components. You can't just say pi equals pf and make this one positive and make this one negative. You can't do that. If you're on one axis, you can, but if you've got a north and a west, that's two axes. And we got to break it up. It's beyond the positive and negative now. Where's the wreckage going to go here? If these two cars stick together like it says they do, where's the wreckage going to go? General vicinity. Yeah, somewhere up here, north and west. All right, let's break it into x components and y components. Say M1, actually, let's say 0 plus M2 V2I. Why did I say 0 for object number 1? Is it moving? Not on the x-axis, it isn't. The combined mass here is 2,700 kilograms. We've got to use both masses because they're both moving on the x-axis after the collision. This works out to be 6.666. Negative, actually, 6.666. Use a y component in a similar way. 1,200 times 10 plus 0, because object number 2 isn't moving on the y-axis. 2,700 kilograms times VF. VF works out to be 4.4. So let's combine them here now. 6.67. 4.4. Solve for V and solve for theta. V is the square root of 4.44 squared plus 6.667 squared. And theta is the inverse tan of opposite over adjacent. V works out to be 8.0 meters per second. And theta works out to be 34 degrees. This would be north of west. If you had drawn it the other way, right, this way, you would have gotten not 34 degrees north of west, but rather you would have gotten an angle of, what would have been, 56 degrees west of north, which also would have been correct, right? Equally as correct. Okay? Yeah, it is. It is. Question was, wouldn't the speed have to be bigger than the other two sides? It is, right? We got 6.6 going one way. We got 4.4 going the other way. It's not going to be bigger than both of them combined. And whatever. Okay. All right. So your homework here for Thursday is worksheet number 4, questions number 1 to 3. There's 7 questions on that sheet, I think. You only have to do the first 3 for Thursday. And remember, earlier today I assigned practice question set number 4. That's homework for today, for tomorrow.